Hello, welcome to Matter Over Mind. Welcome, my name is Stephen, and as always, my favourite future son-in-law,
Hello.
Thomas, is with me today.
How you doing?
I'm very well, and you're hot foot back from your exciting experiment. So,
Yes, indeed.
the last time, listeners, you heard Thomas, he was just about to go on his travels to do his actual experiment that he's writing his PhD on, and it's all happened, or at least sort of half of it's happened. So you had a bit of an eventful 2 weeks. So do you want to tell us a little bit about the stuff surrounding it, and then you can tell us about the actual experiment?
Yeah, sure. So I guess just to explain I'll get to the drama of doing an experiment like this a little bit later.
Yeah. Okay.
But I guess first I'll sort of explain what it is I do. What is my job?
Okay.
In general, what I'm interested in, or I guess what my research group is interested in, is how heat conducts in a plasma that sort of is strongly magnetized, basically.
Okay.
So why this is sort of interesting, a lot of plasmas in space, for example, like astrophysical plasmas, notably like the plasma that surrounds galaxy clusters, the intracluster medium it's called. That's generally strongly magnetized because you have a lot of strong magnetic fields inside, and there's sort of a lot of turbulence going on. And because it's turbulent and there's these sort of what are called stochastic magnetic fields in these plasma, it's difficult to predict how the heat will conduct through it. So I'm probably jumping ahead a little bit here, but basically, if you look at the temperature of galaxy clusters and galaxies in general, you can predict using our current sort of understanding of how heat flows in materials, but they don't quite match up with that. So you can make amendments to include magnetic fields, and they kind of alter it somewhat, but they're still not quite covering the full picture. They're still not quite explaining what's actually going on.
Okay. So let me just feed that back to you, and you can tell me if I get it. So first of all, we're talking about galaxy clusters. So maybe our listeners haven't come across that before. So obviously we know that there are galaxies. We are in the Milky Way galaxy, the sort of spiral form that we're very familiar with, but there's lots of other types of galaxies. But then there's this thing called galaxy clusters. This is where you have a group of galaxies, I suppose, that cluster together.
Mm-hmm.
And you're saying that there's like plasma around the outside of a cluster. That must be huge.
Yeah, it's called the intracluster medium. So yeah, there's stuff between the galaxies, and this is generally very low density plasma. Normally, it's sort of mainly hydrogen and that kind of stuff. But yeah, most of the matter in the universe, not accounting dark matter, is plasma in some form.
Okay.
But yeah, so if you
and plasma is you did tell us this before, but just remind us of the definition of what plasma is, Thomas.
It's a charged gas. So basically, imagine you have a gas, but the atoms have some of their electrons removed. So now there's a net charge.
Okay.
Yeah.
Right. Got you. Yeah.
So the result of that is you can. Understanding how air flows through a room, for example, you just use your fluid dynamics equations and you can kind of understand what's going on there. But if you add a charge into it, then suddenly you have to take into account electromagnetism. So obviously charges repel each other or attract each other in the same way as magnets do. Moving charges create magnetic fields and so on. So there's a lot more. Yeah.
So this helps us to understand how plasma is behaving, and what you're trying to do the field that you're interested in is understanding how this plasma behaves, and our current calculations don't tell us everything. Is what you're basically saying, but the results we get show that there's some stuff we don't really understand. Is that right?
Yeah, pretty much. So there's a pretty nice example, I guess. That is again, like with all these podcasts, there are many caveats and footnotes and so on. But so one of these sort of examples that is thrown out is if you look at what are called active galactic nuclei, which maybe AGNs you've maybe come across. But basically, these are these are, I guess, galactic cores that are shooting out X-rays, and then they've got sort of the sort of what's it called, the surrounding plasma is coming in, and then the current idea is basically the core shoots off X-rays, that cools it down, then the plasma that's surrounding it falls in, kind of reignites it, and then it shoots out more X-rays. That's the sort of general model. So you can kind of see these if you just Google AGNs.
Okay.
Basically, yeah, it's just strongly emitting X-ray sources. So if you look at how much X-rays these things are emitting, you can work out how much plasma needs to fall in for it to get reignited, so it can keep emitting, basically. And for this to happen, assumptions need to be made about the conduction model. So how heat flows. Obviously, if something's cooling down and then stuff is falling into the hot stuff is falling into the cold bit, you need to understand how the heat is flowing, and the way our conduction works. It sort of suggests that these galaxies should be cooling down a lot quicker, and therefore will die out sooner. Basically, obviously, galaxies still exist; they haven't all, burnt out. So there must be some assumptions there to suggest that maybe something's slowing down the conduction of heat.
Okay.
Obviously, this is grossly oversimplified, but just for argument's sake, basically, these galaxies are throwing off a lot of X-rays, a lot of radiation, so it's cooling them down quickly. So more material has to fall in than there is. So in principle, they should have burnt out long ago, but they haven't.
Okay.
That's like I said, the caveat. But so that's one example.
Okay.
To why heat flux is important, or understanding how heat conducts is important. Another place, obviously, is ICF, inertial confinement fusion.
Right. This is what we talked about earlier. Yeah. Okay.
Yeah.
So understanding this helps us understand fusion a bit better.
Yeah. Well, I mean, generally, heat conduction, knowing how heat flows through stuff, is useful. But for fusion particularly, obviously, you want to keep your fuel as hot as possible. For as long as possible, so it can reignite and begin fusing. And I guess why I'm interested in magnetic fields, which is something I've not touched on yet. So it turns out when you shoot your capsule, your ICF capsule with your lasers, and you crush it down, there's a point called the stagnation phase, and during this point you get really strong generation of magnetic fields. So there's this interplay now where really strong magnetic fields get formed during the implosion of a capsule. Also that heat conduction is important. We need to understand how heat flows to keep, so we understand to keep it hotter for longer. But we don't quite understand how heat flows through a medium that has these strong stochastic magnetic fields.
Right. Okay.
So that's kind of where it loops back into fusion. So in galaxy plasmas, or intracluster galaxy plasmas, because of the turbulent nature of the plasma, you get generation of these magnetic fields. So heat flows, or heat may flow in a strange way up there, but it may also flow in a strange way on fusion scales because of this generation of strong fields. So that's, yeah.
Wow. So I mean, that is so interesting, isn't it? When you think about what you're doing there, you're working on something that might help us understand these behavior of these huge, great structures, clusters of galaxies. But on the other hand, you're also working on the same thing that helps us to understand how this plasma and these magnetic fields are behaving in that very, very precise, very small pellet that we're firing. Listeners, by the way, if you've not already checked it out, on the Facebook page, I put a few pictures, and we can actually see there's a picture of one of the capsules there that I think you commented on that as well, Thomas. It's tiny, but you can see it, and it's held in between two fingers, so you can see how big it is. It's just amazing that you can get that much energy out of that, isn't it?
Yeah, it's really cool. So there's another thing also that's observed in astroplasmas that also kind of might be kind of links into what I'm seeing. You get what is called cold fronts, where you see and basically if you Google X-ray temperature map of a galaxy cluster, you'll probably see exactly what I'm talking about. But you get this kind of speckle pattern of the temperature where you get hot spots next to cold spots. and this is kind of scattered throughout the the temperature of the system, and this is sort of counterintuitive, right? You would imagine if something is hot, you'd have a central hot spot, and then you get sort of uniform gradient, uniform diffusion into the colder surroundings, right? That's kind of
Yep.
the intuitive picture, but that's not what happens. You have hot next to cold, next to hot, next to cold, and there's something stopping it, there's something trapping the heat, which is another interesting thing.
Okay.
Which also could be explained away by sort of introducing magnetic fields into your system. So, okay, to talk a little bit about magnetic fields, because I've mentioned them a few times. So I'll explain a little bit how they can affect heat. So we know that quite well, actually. So I mentioned many episodes ago, if you have a magnetic field, your electrons will gyrate around that magnetic field, right?
Yeah, remember that.
So in a plasma, not always, but in the kind of plasmas I'm interested in, the dominant source of heat conduction is due to electrons. Basically, you can imagine your ions, which are your sort of nuclei, your atoms that have been stripped of electrons. Those guys are very heavy and slow by comparison, so you can kind of imagine them as just sort of sitting there stationary. And the electrons are a lot lighter, so they kind of travel through. So how the heat flows here, in this, I'm specifically talking about heat conduction, which is different to convection. So convection is what you might hear when you learn about radiators. It heats the hot air moves up, and the cold air displaces it. So that's basically displacement of a energetic medium to a different location, and then heat is moved from A to B. So that's convection. I'm talking about conduction. Conduction here is, imagine it like a collision of things transferring energy.
Okay.
So imagine the wind blows you, the cold air touches your skin, it takes away some of your energy, and now you're colder. So it's a transfer of energy via collisions or interactions.
So I'm imagining a set of billiard balls or a set of snooker balls, and you hit the first one. They're all lined up, touching each other. You hit the first one, and the last one is moved. Is that so? The energy is conducted through the different billiard balls. Is that right?
Yeah, you can imagine it like that. Yeah. So you've got initially a cold system where the ones that you've not hit yet are stationary, not moving, and then the one that the billiard ball that you hit with the cue, that's now the energetic particle. It hits the other billiard balls and it transfers some of energy. In return, it slows down some, and the other ones now have some motion.
Okay. Yeah. Okay. Cool.
So as I said before, magnetic fields, the electrons gyrate around them. We now know that electrons are the bulk source of the heat flow in the material. Basically, what happens is electrons flow through because they're a lot lighter and quicker. They have a lot more, they can zoom around a lot quicker. They kind of collide with the ions in the plasma and other electrons, and then it heats up the system, basically. And then you can imagine that spreading outwards, right? Kind of like a wave, But when you have magnetic fields now, so now imagine if the things that are traveling around your heat that were originally randomly, scattered about, now you've got a bunch of magnetic fields, you've got a bunch of railroads through your plasma. Now all the electrons are bound to that. So all the heat is going to flow basically in one direction, right? And so that's one way magnetic fields can be used to sort of alter how the heat conducts in your material. This has actually been tested in ICF experiments, where they set up their experiment. They put a really strong magnetic field through their fuel, and then when they imploded it, they noticed basically because the heat could only escape in one axis instead of in 3D. They outputted higher neutron yields and also higher ion temperatures. So they had a hotter fusion plasma by reducing the areas where heat can escape from. So you're kind of insulating. It's a kind of an insulation mechanism.
Okay.
So great. You're probably thinking, well, what's the problem? We've got it solved.
We know it already.
We know it. Yeah. The tricky part comes when your plasma becomes turbulent, or when you have sort of non-uniform fields. If the railroads are in a straight line, you can kind of predict quite easily what's going to happen. But imagine if your railroads turn into a tangled mess. Now it's suddenly a lot harder. So an experiment actually that sort of is kind of like the predecessor to the experiment that I've just done a couple of years ago. That was on a National Ignition Facility, the NIF, and what they showed is they generated a plasma similar to what you'd see in galaxy clusters, and they proved, or they showed the first like laboratory evidence of suppressed conduction. So they produced a plasma, and it had these sort of hot spots and cold spots like you see in galaxy clusters, and they deduced that it was almost certainly due to the magnetic fields in the plasma. So they basically made a turbulent plasma by shooting some stuff with lasers, sending it through some grids, and then it sort of broke up the plasma. And then when the plasma collided, it kind of became turbulent or had some strong mixing. And there are some methods which I won't bore you with, but you can sort of embed magnetic fields into your plasma. And so they kind of generated a plasma similar to what you'd see in galaxy clusters, and then they basically took a picture of the temperature by looking at its X-rays, and they showed you had hot spots next to cold spots next to hot spots, which contradicted the simulations with with our current models of physics, where the simulations showed you'd get a hot spot, a big bright hot spot that would then cool off uniformly, but what they saw was this sort of speckled pattern of temperature.
Okay.
So it's not just we've seen some stuff in space and we've thought about it. We can now generate in a lab similar conditions.
Right. And it's this turbulence that is the factor that we don't understand how that affects the this conduction of heat within the plasma. Is that right?
Yes. Well, yes and no.
Okay.
Yeah.
I rarely get it all right. The best I can hope for is kind of. That's what I normally get.
So I guess why turbulence is important is once you have a turbulent system, a lot of complicated stuff starts happening. And the other interesting thing about turbulence is it's what's called scale independent. So in principle, you can scale down or scale up a turbulent structure, and the dynamics is the same basically.
I suppose the word turbulence. Most of us will be aware of, or familiar with the phrase or the word turbulence when we're flying in an aircraft, and they say we're approaching turbulence. So it just means kind of, I suppose, disturbances in a in the air. It would be obviously in the wind and so on, but it's like I guess it's hard to predict how turbulence behaves, because it seems quite chaotic, doesn't it?
Yeah, well, that's another way of describing turbulence: chaotic mixing. Yeah, you have imagine you've got a liquid and you kind of just run a spoon through it in a kind of a random way. You're gonna have some strange mixing. So obviously you can imagine, sort of the fluid folding over itself and stretching itself, and that does, wacky things to the plasma. So turbulence was basically recreated. Well, funnily enough, actually, that experiment, or that set of experiments, wasn't massively interested in heat conduction originally. They were testing something else. They were testing how magnetic fields can grow, because you get magnetic field amplification in galaxy clusters. There was always some thoughts of what's this going to do to the conduction, but it turned out when they were doing these experiments, that's when they thought, actually, so we've created a plasma where we've shown that you can amplify these magnetic fields, but let's look at how the heat flows through it. And that's when they found, actually, it's not flowing. it's kind of staying hot in a way that you wouldn't expect.
Right. Okay.
Or rather, that is hard to predict with our current models. And basically, so they kind of showed that it was due to how the electrons were magnetized. But because it was turbulent, and that sort of adds a chaotic complexity, it was difficult to basically find out why. What about the magnetized electrons, or caused it? So there are things called mirrors, magnetic mirrors. So this is where you have a really strong field followed by a weak field followed by a strong field, and your electrons can basically bounce back and forth in those. So that would be one way, for example, of heat being trapped in your system. And there's a few other possible reasons why it could have been insulated, basically. So that's where we come in. That's why we designed this experiment, to basically make a plasma that wasn't turbulent, make it effectively a simple plasma, but that still was, hot enough and magnetized enough that it could still produce one of these mechanisms that could suppress the conduction.
Right. Oh, okay. Okay. So you're removing that that element that makes it difficult to understand what's happening, so that you can understand the process better.
Yeah, exactly. So it's no argument now that when you have strong magnetic fields in a turbulent plasma, that is also, has low collisionality and high beta, which is just some other caveats. If you have a plasma that meets those conditions, it will suppress the heat conduction. Like that's
Okay.
We've shown that in a lab now. All the theory points to that being true. We're pretty happy with, but why?
Okay.
Why is the question. So this is kind of it's a good point for me in time now, because technology has caught up to us. We can now do these things in a lab.
Right.
So, a lot of the theories that I'm looking into and testing, they're 20, 30 years old. They're quite old theories. But it's only fairly recently, in the last decade or two, that we've been able to make facilities that can produce these plasmas, which is really cool.
Wow.
And it's in some part, I guess I'll give credit to one of the major laser advancements that's happened. I say in recent times. The Nobel Prize in 2015 was for this. It's called CPA, chirped pulse amplification. So what this technique is, it's a way to amplify the sort of laser intensity to ridiculous orders of magnitude, more than we could before.
Yeah.
So this is a bit of a tangent. This isn't really my research, but I'll talk about it anyway because it's cool.
Okay. Yeah, that's cool. Yeah.
So when you have a laser, what this means is all of your light in that laser is the same wavelength, so it's all the same color, and it's the same frequency. So it's monochromatic and it has the same frequency. Unlike if you shine a torch, if you put the torch through a prism, you'll see a rainbow. If you shine a laser through a prism, you'll see the same color. So when you put it through lenses and mirrors and stuff, you can stretch and increase the intensity of your light. You can increase the power stored in your beam, but there's a limit to that. You could do this via physical lenses, so bits of glass or crystal or whatever. But there's a material limit to how much you can amplify before your lens cracks.
Okay.
So you can't in principle increase a laser power indefinitely if you have a big enough crystal, because the crystal will break. There's a limit. So what these people figured out was, if you put your laser light through what's called a diffraction, well, it's probably not called that, but through a grating sort of made of crystals, you can through different points in the laser beam, you can kind of stretch the light such that they're different wavelengths, and then you can kind of send them in different directions. So you send in one laser light, you kind of split it up into, say, 5 or 6 sub laser lights and stretch them differently, so they're now different colors. Then what you can do is you can pass each of these colors through their own lens to amplify them, amplify each of these beams individually to the material maximum, and then put them through another grating and reconverge them. So you basically, and then with that you can, multiple times
Increase power.
Yeah, just increase power, but by splitting up one beam into several beams, amplifying those to the maximum, and then just smushing them together.
How clever!
Yeah,
and that technique is something that happened that we learned how to do about 10 years ago, and that's allowing you to do your work effectively.
Yeah, I mean, it was discovered a while ago, but the Nobel Prize was won in 2015. So it'd been around for a while before that, but that's an example of a technique that has allowed us to. There's been other advancements, but that's the kind of big one. If you Google laser advancements, CPA is the big one.
So how did your so you've told us a bit about what you're trying to do. Is there anything else you need to tell us about that first before we get into your experience on the actual experiment?
No, I think that's mostly it.
Okay.
Basically,
All right.
yeah.
Tell us how it went then. What happened?
So it was a 2-week campaign.
Yeah.
With the plan to get a total of 24 shots of the laser,
Yeah.
which doesn't sound like a lot for 2 weeks, but you got to wait for it to cool down. So,
Okay.
so week 1, I get there. Day 1's just going to be sort of setup, calibration, that kind of thing, and then they're saying, "Oh, okay, we've had issues with calibration. We'll spend some of tomorrow continue calibrating, so you'll lose half a day." Okay, fine. The next day happens. Oh, we're still calibrating. There's still issues. Okay, fine. And then it gets to sort of like 3-4 o'clock. They're still calibrating. We're thinking, okay, we'll just come back tomorrow and see what happens. And then, so we have an early day. As we're leaving, one of the beamline scientists comes in. Catastrophic error. One of the high voltage cables has basically blown up, sending arcs all over the plasma, the laser chamber. So obviously they have to shut everything down.
Right.
To understand why that happened in the first place, and 2, to assess the damage if there is any. So Wednesday, I'm sitting in my hotel waiting for the call back, and then I get an email.
Yeah.
Go home for the week. We'll try again next week.
Oh, God. Yeah. So we, I didn't want to sort of hassle you, by keep texting, but I think I sent you a text say, good luck and everything, and then we got from Celine that you were back home again. Devastating.
Yes.
So I bet you were pretty fed up at that point.
Yeah, I was pretty gutted because we've been planning this experiment for like 1.5 years now, and as you said at the start, it's going to make up the bulk of my thesis. So whether it goes well or goes poorly, that doesn't matter physics wise. But it needs to happen.
Got to have something to talk about.
Yeah, exactly.
Yeah, absolutely. Yeah. So, so you lost that week. You go back again the following week, and so we're talking now after you've had that week and you've been able to do some work. So that's good. So tell us what happened there then.
Yeah. So this week actually was the first day again just calibration stuff, and that was fine. But we had been rest assured that everything was good. And then it comes to the Tuesday, which is the first day of planned shots, and we're all in the control room waiting, and they've got the our little target, the thing that we're turning into plasma.
Yeah.
That's in the chamber. It's on the screens, we can see it in there. Then the shutters go down so the cameras don't get damaged, and then sort of 6 or so bars appear on the screen and they start filling up. We're like, okay, good. They're charging the capacitors.
I bet your stomach is churning, isn't it? I bet you're so nervous.
I was quite nervous. And then they get to about 1/3 of the way up, and then they don't. And then all the scientists are like, oh. And then me and my supervisor were like, what does that mean? What's going on? It didn't fire. We'll have to wait 6 more minutes before we can try again. Right. Okay.
God.
So we wait again.
That's the longest 6 minutes you've had, I suppose.
Yeah, it is, yeah. And then the bars start climbing. Get 2/3 of the way up, they come down again. It's like, right. And then they're like, if that happens one more time, we're going to have to shut the laser off and then just see what's going on. I'm like, oh, come on. God. And then the 3rd time, they charge up. They get to full, and we get our first set of data. It was exciting.
Wow.
Yeah.
Wow.
It was very stressful the first 2 times. Because when they said if it happens 3 times, we have to turn it off. We were all like, no, I can't go home again. So it was quite stressful. But after that, we had no issues. It was all good.
Oh, okay. So that was weird then, isn't it? That's just somebody's trying to play around with you.
It's
okay.
It's unfortunate I say unfortunate. These places are so complicated and there's so many moving parts. There's always bound to be something that goes wrong. Normally, if one thing goes wrong, it isn't the worst thing in the world. You can kind of make workarounds, but obviously charging the capacitors, that's where the power comes from. So those need to be full before you can turn it on.
Yeah. Okay. So you obviously then you were able to do some more shots in the week, but I guess you weren't able to do as much as you'd hoped for. So I think you're hoping to go back again and just sort of finish off a bit later if you get opportunities. Is that right?
Yeah, exactly. So we got we got some good stuff,
Yeah.
which is always nice. But there's a few more bits that we kind of need to put the nail in the coffin.
Okay.
So, like I said, we can make a pretty good argument. Well, obviously, I've not analysed any of the data yet, but looking at what we've got, we should have enough to be able to talk a little bit about what's going on.
Okay.
But to really kind of drive home our point, we need some more. Well, more data is always nice. I mean, realistically speaking, most experiments, or most anything really, any sort of scientific investigation, the more data points, the better. I mean,
Yeah.
24 being our maximum still isn't many. If you think about it, 24 lots of data isn't that much data.
No.
And that's the way things are for these high energy density experiments. You don't get a lot of data.
I mean, to be honest with you, Thomas, in psychology, you wouldn't be able to get away with that. If you just had 24 participants in an experiment, you'd say there's not enough people there. So I don't know what you're saying.
Yeah, you're right. It's I'm a poser. I'm a phony.
So when you say data, what are we talking about? Are we talking about numbers on the screen? Are we talking about pictures? What are we talking about?
So we're interested in a couple of things here. So obviously, one, we need to know how hot it is, the temperature.
Okay.
Because that's we're doing a heat conduction experiment. We need to know how hot it is.
Yep.
But because of these plasmas, I mean, the kind of temperatures these plasmas are getting to, we're talking like sort of 10 to 100 million degrees. They're very hot plasmas. So you can't just put a probe in there and read it off a monitor.
It's not like making a cake, is it?
No.
Is it ready yet? No. So how hot is it's hotter than the sun, isn't it? That is. It's absolutely.
So the surface of the sun is about 6,000 degrees. So it's quite a bit warmer. It's sort of comparable to maybe even a bit more than the core of the sun, temperature wise. So it's really hot, this stuff. So yeah, like I said, you can't just plug a thermometer in. So there's a few ways you can measure temperature, but one of the most robust ways for this kind of plasma is looking at the X-rays, looking at how much light it gives off.
Okay.
Generally, the brighter the light indicates roughly how dense it is, so how much stuff is there. Obviously, if there's more stuff, there's more light being given off, so it's brighter. But then basically the color of the light tells you what temperature it is, basically.
Okay. So
I've mentioned before about the shelves in quantum mechanics. You've got the energy levels. If an electron drops from a higher shelf to a lower shelf, that's a set energy gap. So that'll give off a photon of a very specific frequency. So different elements have different shelf spacing. So if you know what material you're looking for, in our case, we're curious about chlorine. We know for a given number of electrons in chlorine, we know what photon energies they're going to give off, what color they're going to give off, basically. So that's one way to look at it. So we can look at how bright the thing is by taking a picture of the X-rays, and then when you put it through a prism, you can be like, okay, cool, is there more or less of that frequency of chlorine light, for example, and that can indicate, okay, if there's more of it or less of it, it's this hot, because when chlorine's that hot, it gives off this much of that light, this much of that light. So that's also a way how they know what materials are in stars and stuff.
Okay.
So you look at the emission of a star, you put it through your lens, and then you see what lines are missing. So certain lines missing implies there are materials in the sun that absorb that wavelength. By basically looking at either what lines are emitted or what lines are absorbed, it can tell you what's in the plasma, and the wavelength of that line or the position of that line in your frequency tells you basically how hot it is.
Okay. So you're measuring the heat. What else are you looking for?
So we're also interested in magnetic fields. That was the second. That was the second thing. We need to know if magnetic fields are present. Otherwise, it could just be some other reason that it's cooling in the way it does. Magnetic fields. There's generally two ways you can kind of measure magnetic fields in a plasma. There's something called Faraday rotation. Basically, the magnetic fields can polarize the light in a particular way. That's a sort of older method and it's useful for some plasmas, but for us it's not massively accurate for reasons I won't get into. The other method is called proton radiography. So this is actually, I really like this technique. Basically what happens here is you generate a beam of protons. The protons travel through your plasma, and because protons have a positive charge, the magnetic fields in the plasma deflect the protons. And then the picture you measure, it kind of looks like, like the bottom of a swimming pool. You see those caustics, and it kind of looks like that. And then you can work out what magnetic field would have to be there to deflect a proton to make that pattern. So you can basically back out, you can reverse engineer a magnetic field that would have to exist to cause that deflection.
Okay.
So yeah, so those are the two main things sort of we're using. We're looking at the X-rays, or how hot the thing is by how much light it's emitting, and then we're looking at the magnetic fields by shooting beams of protons into the plasma and seeing how they get deflected.
Cool. And so you're in your you're halfway through your PhD now, is that right? So you've got over a year to do all this this crunching of the data and obviously writing it all up. So that's kind of what you're going to be doing over the next year or so, yeah?
Yeah, exactly. So I've already drafted a paper on the design of this experiment. So it's a chunky 23-page or so paper.
Okay.
It still needs to be edited and sent to the collaborators and stuff. But
so you're going to release that one first. You're going to have a paper that's just how you set it up.
Yeah, basically, it kind of think of this as like the simulation proof of concept paper. Yeah. So that will be published hopefully in a few months. But yeah, that'll probably go first, and then in about 6 months to a year's time, hopefully I would have analysed the remaining data from this experiment, and then I'll write up the results paper for that. Right. And then those two papers. There's a couple other papers I want to write, but that's not quite to do with this, so I won't bother mentioning that.
So this is your main thesis.
This is
your PhD.
This will be a solid maybe 70% chunk of my thesis, and then the remainder are the other bits that I'm working on on the side. But yeah, so this is a big bulk of it. So the goal of what I guess I'm trying to look into is, how do magnetic fields affect plasma? Specifically, can we see it in a lab? That's the main thing.
And is this sort of fundamental science in that we don't necessarily know how it might be used, or there's no sort of clear this is to enable this thing or that thing, or are there ideas around what this could help us with? Obviously thinking about nuclear fusion in particular, but what sort of possible advances might this sort of thing help us understand?
So this kind of research comes under what's called fundamental research. So in the sense that I can't, with my data, I can't then give it to a company and then they've fixed fusion. So it's
sure.
Probably how this, providing the experiment, providing we prove true that our hypothesis, I should say, probably how this would then work is we'll have some data that confirms a few theories, and then what they will do is, okay, cool, bin some of the other theories. We know this is kind of how it is now, and then it would likely end up going to update some simulation codes. So then when you design future fusion experiments, for example, you can be more knowledgeable of the kind of things you might have to look into. So that's probably how it would go. It'll confirm or deny some theories on how heat flows. Then those will go to update simulations, which then can be used to design better experiments and more efficient experiments and so on.
Okay, that's cool though. So it could help produce better results for fusion in the future. So that's cool. I mean, this is how science works, isn't it? So there's lots of little bricks that you learn something about this, and you lay that brick, and you learn something about that, and you lay that one, and then gradually this builds a picture that we can then build on. So that's part of the process. That sounds fantastic, mate. Yeah,
brilliant. It's cool. And other than applications, as as just an academic exercise. As it stands at the moment, we don't know how heat flows through materials that meet XYZ criteria. We probably should know that. So I guess that's another way of thinking about it. It's something we don't know, that we engage with quite a bit, but we don't know at all how it works. So
yeah. Sounds good. And for the Starship Enterprise, when you hit those phases, you want to know how it's going to behave. If there's a magnetic field in between you and the Klingons, you definitely want to know that.
Exactly. Yeah.
Otherwise
you're going to get polarized phases, and they might not resonate with the shields
might not
properly.
work.
Yeah.
Certainly. Yeah. Okay, brilliant. So that sounds really exciting. I'm so glad that it all went well on your second week. Anyway, I was really anxious about what you were going through on your first week. I know a lot is, you can get around anything really, but feels like quite a lot is riding on that 2 weeks, because it's part of this 3.5 year journey you're going on.
Yeah.
Obviously, people can, once your paper is published, then you can look on Google Scholar, and you might be able to find a way of accessing it. So that will be a very exciting moment. We'll let you know when that happens. In the meantime, you can post questions on the Facebook group. If you've not become a member already, then don't forget to do that. It's a nice little group. We're getting a few conversations going as well, but and also ask questions, post your own sciencey stuff on there if you want to, pictures of stuff, and we try to put some supporting material on there. So Thomas, if you can maybe pop a few things on there that you're able to, that would be quite cool from today's episode.
Yeah.
So keep talking to us and asking us about this stuff. Okay, great. Well, thank you very much, Thomas. That's been great. I really enjoyed that, and I can't wait for the paper to be released. I mean, I've read some of your work that is, still in its sort of development phase, and I don't understand it all, but there are some bits that I did understand, and there are some very nice pictures as well. So it's fantastic work. And I know you're really excited about it. So thank you again for telling us about it.
No problem. Glad to talk about it.